Right, so in the balloon FET that you just did, you learned about conservation of charge, right? Where the charge, right, charge has to go somewhere. Meaning charge can be transferred, but it can't be created or destroyed. So yeah, same thing as energy, mass, momentum, right? So with conservation of charge, the charge has to go somewhere. There's a finite number of charges in the universe, right? Kind of crazy to think about, but in the universe there's a finite number, right? And they may go all different places, but the number is still the same. Okay? One of the things that you said was, all right, when I took the balloon and we rubbed it over the shirt, the electrons jumped onto the balloon, but we couldn't get it back onto the shirt again. That has to do with that thing, the electrostatic series of conductors. That means that what we saw was that the rubber will steal electric charges. Okay? It steals the charges. That means it can't give it back. All right? When you're talking about rubber and cloth, the rubber is a thief. Thieves don't give stuff back unless they're caught. Right? And these guys don't ever get caught. Okay? So, really important right there is this conservation of charge, is that whatever one loses, the other gains. So if you have 10 charges on each, okay? So if you have this box that has, let's even call it 4 charges. Oh, and then minus, 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 minus. And this guy has something like that. When they come into contact with each other, oh, my board needs to be redone. It may have something now, 5, 6, 7, 8, where the ball stole it from the box, where you used to have 4 positives, 4 negatives, and then 4 negatives over here. Well, now the ball stole, actually it should be 6, never mind, we'll just ignore that. Now this stole it, right? So because there were 8 total negatives, there still has to be 8 total negatives. They just may be distributed differently. Does that follow me? Okay. That's very simple conservation of charge. All right. You can classify objects into 2 different things for the most part. You can have a conductor, right? In a conductor, electrons flow easily, or they move easily. Okay? You put electrons or charges on a conductor, and they move very nicely. Okay? They actually spread out. Okay? And they'll spread out until all the forces that they apply on each other balance out and they can't move. Okay? For an insulator, any electrons that you put on the insulator, they become immobile. So one of you mentioned when we talked about the balloon was that wherever the electrons touched the balloon, that's where they stayed. Right? So you could have one side of the balloon that had charges on it, one side that didn't have charges on it. It's because that balloon was an insulator. So you could put them on there, but they weren't allowed to flow. They weren't allowed to move. Okay? Imagine, you splattered a balloon with some paint. Wherever the paint went, those would be the electrons, and they're not allowed to flow around it, to spread itself out. Okay? And this becomes really, really important. Okay? What types of materials do you think are conductors? Say that again? Oh. Yeah, metals. Metals are really good conductors. Your worst conducting metal is thousands of times better than your best conducting non-metal. Crazy, huh? So when we're talking conductor, we're talking, aluminum, steel, gold, copper, all very good conductors. Gold is an excellent conductor. How come your house is not wired in gold? Really expensive. Really expensive, right? Copper's like a happy medium. Some houses are actually wired with aluminum wire. A lot of my house is, because it's cheap. Insulators, what do you think what insulators may be? Rubber, what else? Wood, yeah. Plastic, right? The thing is that mostly non-metals are good insulators. They don't allow charge to flow through them. That's why you take a wire, and that's why it's metal wrapped in a plastic, right? So that the electrons flow through the wire, but the plastic keeps them locked in so that you can handle the wire, so you don't get zapped. That's always a fun experience. Okay? So you could have like uninsulated wire. It's a little sketchy. It can happen though. Try it sometime. Stick your tongue in it. All right, so types of charging. How can we move electrons? So charging means how can we move electrons from one place to another? The first is through contact or friction. That is literally rubbing two objects together. Okay, and you rub those two objects together, charges transfer from one place to another. Easy, right? Easy peasy. The next you could have is polarization. In polarization, what you get is a slight separation. Right, so when you brought the balloon near the wall, did you notice that the negatives ran away from the balloon? Right? But overall, the wall stayed neutrally charged. Okay? That's charge polarization. So when you bring a charged object like up to the wall, the electrons were repelled because you have electrons on the balloon and they wanted to, repel. They follow the same rules as always. Right? But they're still locked in as neutral in their atom, right? In the object, in the wall or the object, whatever it may be. And the positives have to stay. So you had in the wall positives here and negatives over there. Right? And then so these electrons here repel the electrons over here, but overall you're still negative. It just so happens to be that now this part of the wall is a little more positive, and this part of the wall is a little more negative. But it's still neutral overall. Does that make sense? Okay? So that's polarization. You have now created poles. Okay? You guys talked a little bit about polarization and polar molecules in chemistry. Right? Water's polar. Right? So one side is a little more positive and one side is a little more negative. Okay? The last one that's that we can talk about for types of charging is called induction. Induction's a little weird. So in induction, you're charging something without it even touching. Right? So you're going to take some objects that are here, and you're going to bring something charged in, and they don't, and it becomes charged, and you never touch the two objects never touch. Okay? It's a little weird. I got a picture. It's the best way to describe for you to see it. I got a picture that will show you what it looks like. So here we have two metal spheres, right? They call them spheres A and B. And the spheres are metal, and the stands are insulating, so that all the charge goes onto here, and that's it. Okay? We then bring this charged object. It's positively charged. I don't know what it is. It's weird. It's just like a red positively charged blob-ish thing. Okay? We'll call it a charged Strauss. And it brings it in, right? And these are both neutral, but they're connected. So things can flow between them, right? That makes sense? Okay. Well, if this is positively charged, it attracts the negative, right? Does that make sense? It attracts the negative over there. So while these two things may be neutral together, this side now becomes more negative, this side becomes more positive. Follow me? Okay. Then what you can do is your friend comes and separates them while this charged object is still near it. So it's still pulling on these electrons. So now this sphere has become negatively charged, and this sphere is now positively charged because, again, this positive blob thingy pulled the negatives across. And once you separate them, there's nowhere for them to go. Right? There's no path to get back. The key is this has to stay in the area. Because if you pull it away, the negatives are going to go back and spread out between them. Okay? And then, once you've separated them, you can pull the charged object out of there, and now A is more negative and B is more positive. And you've charged them, but the object never touched it. All you've done is rearranged the charged objects. Okay? And that's induction. It's a little weird, but it's kind of cool at the same time. Okay? When? Like up here? It would suck them up this way. And it wouldn't, right. It wouldn't change the distribution. Yep. Yeah, you got to go on the sides so that you get everybody on one end. Okay? Make sense? Okay, awesome. So let's get to our last bit that has to do with electrostatics. And this is pretty quick. Oops, I want to go over here. Writing in red, and I didn't even know it. All right, so the last thing is Coulomb's law. So again, with the balloon thing that you did, you told me that the closer the charged objects got, the faster they repelled, right? So there was a greater force acting on them, correct? So there was a greater electrostatic force. The way that we determine the magnitude of that force is through a thing called Coulomb's law. And this is Coulomb's law. It's just F equals K1, K, Q1, Q2 over R squared. K is just a proportional number. It's just a constant value. 9 times 10 to the 9th. Okay? So K is just 9 times 10 to the 9th. Anytime you see K, just plug the number in. Okay? The Q's are the value of the charge. Okay, we use the unit of the Coulomb, which is a capital C, as the unit for charge. So if I say, you have a charge of 75 coulombs, that means you have 75. That is your charge. Okay? 75 coulombs is a ton. A ton. If you touch something that is 75 coulombs, you will die. I promise you. I promise you. That's like a ton of electrons. Okay? A lot. And R is the separation distance. Okay. You notice this is obviously then follows the inverse square law, meaning the closer something gets, right? As this number gets smaller, this whole quantity gets larger, right? That's why when the charged balloons got closer to each other, the force was greater because of this, right? Because of this inverse square. Right? The distance between them is the big driving factor in terms of what happens there. Now, does this equation look familiar? Feel like it does? What does it look familiar to? What's that? Yeah. It has the same exact form as gravitation, right? Remember that? It has the same exact form as these two together, okay? And that's pretty cool, right? So what this equation, along with a bunch of other things, has led scientists to believe that there has to be some link between gravity and electromagnetism, because the forces involved, they follow the same style of law, right? Or the same shape law. And one of the big things right now is trying to find how do we connect them? How do we connect the really little things to the really big things? And there are a bunch of different ideas, and they're a little mind-blowing. Maybe we'll learn about them after the test. It's kind of cool, right? So Coulomb's law, really simple. Does it make sense? Okay? Just closer you get, the stronger the force, the farther away, the weaker the force. And keep in mind, this is the magnitude of the force. What dictates the direction? Whether they repel or attract. Positive, negative, or same or different, right? So you could have two positives and they're going to repel. You could have two negatives and they're going to repel, right? But opposites, and that's when they're going to attract. Okay? Does that make sense? Good? So what would you like me to say?
Understand how positives will repel and opposites will attract, but isn't it the force between or two objects?
Any charged object. Not electrons, any charged object. So you could have two positively charged things, and they're going to repel.
So the sign of the force you need to relate to
what their charge is, positive, negative, negative, negative. If you look up here, this is really the absolute value, so we're just looking at the magnitude of these. But if you have positive, positive, you just get a positive force, right? Negative, negative, you get a positive force. So then they're going to repel. But if it's negative, positive, you get a negative value, right? And the negative, you could kind of say it means that they're attracting. Okay? Good? Good? All right, cool.